Hello, everybody. My name is Kevin Kocek. I'm the founder CEO of Chemical Q Device, here to tell you about quantum machine learning neuroimaging. So this is quantum technologies in specific to make Alzheimer's disease images better. So with that, this is the format that I'm going to go over. So basically, it's a progression with quantum machine learning. So this first paper focuses on Alzheimer's disease prediction using transfer learning, which incorporates a lot of classical techniques with a quantum technique at the end. And then in specific, they narrow it down between GoogleNet and ResNet 34. And then also they use quantum simulation. So this is between Penny Lane and Qiskit. So as you could see that, let's see here. You should be able to see this. So, okay. And then we'll go back here. This is the first paper. Now, the second paper is about quantum machine learning opportunities. Now, if you don't have a subscription to Nature, I would highly suggest getting one. It's only $30 a month. Now, this particular paper by Los Alamos National Laboratory is not a free paper, so you do have to pay for it. But it talks about inductive bias and the importance of it with quantum, basically having these interim error solutions in this noisy quantum computing era that we're in right now. And then you also have, quantum data advantage as well. So the last portion will be about Chemical Q Device, in specific, doing potential sensor developments, and then also incorporating quantum machine learning into neuroimaging for Alzheimer's, and also some of the goals as well with the startup. Now, if you haven't been a part of any of these before, the Alzheimer's associations or your favorite Alzheimer's, walk events, is that they're very supportive, high energy. As you can see, they bring in kind of like these, Star Wars characters. People get up on the stage, share their testimony. And, so basically it's a huge thing. So we had a couple hundred people show up, and you can see people of all kinds. And then in the lower right-hand corner, you have Superman taking a picture there as well. So this I've shared before, and it's important to notice that a lot of these things are basically, it's an ongoing process understanding the mechanism. So when you take neuroimages and MRI, PET, CT, these types of things, it's a continual process. So this is a Nature article from 2020, and then it shows kind of the interaction between extracellular tau, soluble amyloid beta plaques, and their effect on microglia and then neurons as well. Now, in the first article here, it's important to point out that you have all of these MRI scans available in databases that know if you have dementia or if you don't have dementia. It's a yes, no on them. So basically, this paper is using aspects of quantum technologies called hybrid quantum machine learning with these MRI scans to get better accuracy, less loss, these types of things. Now, classical neural networks on their own extract the high dimensional features and embedded features into a quantum processor. And again, these are quantum simulators. But it's a good proof of concept paper, because basically it's showing that, gradually incorporating more and more quantum technologies. So you have this hybrid transfer learning, which is basically the vast majority is previously done. And, you're with a quantum circuit improving it in performance on pre-trained ResNet for architecture. And this is currently for small numbers of data sets to, using deep neural networks of fine tuning and feature extraction. So figure transfer learning, in this case, fine tuning, feature extraction. Now, the whole process here is hopefully, some of you are familiar, with this first step is basically a quantum computing. So this is composing of quantum bits. And then the phenomenon, if you have a single quantum bit, you have superpositioning, and this is what is opening up for massively parallel processing, and the entanglement is more like exponential, power as the number of qubits increases. So this is basically, you have quantum gates, quantum circuits, unitary transformation, and they talk about variational quantum circuit a lot. So if you're an expert in this, hopefully this makes some sense. And then if you're not, you can capture this information, basically say, state preparation layer, variational layers, and measure. And then, so the authors of this paper laid this out for instruction. And you have initialization, this embedding layer, variational layers, measurement layer as well too. So as I go on here, is you basically see, this is the first step, is they wanted to compare GoogleNet and ResNet 34. Now, ResNet 34 has been used for Alzheimer's applications before. And, head on head, it's pretty clear that they're choosing this ResNet 34 compared to GoogleNet. For these, obviously, they've done this and they had some prior knowledge that this ResNet is popular for Alzheimer's cases. So basically the thing with this is a public data set, 6,400 later labeled MRIs to train the network. And then specific, these images are distributed into demented and non-demented. It's just two cases there too. So the learning rate 10 to the negative 4 for quantum depth of 6 layers. Now the ResNet 34, it's to extract features from the image and feed a 512 feature vector to the quantum variational circuit. So, this, you'll hear this a lot. And the results, as they're reporting, are very good. So they say training accuracy of 99.1%, classification accuracy of 97.2% for 20 epochs. Now, the model, in their mind, this is one of those like first papers out there, is that, this is way before clinical use, is that it's prospective for speed ups in clinical settings. And the future forecast is basically, larger medical imaging databases for faster hybrid classical quantum machine learning networks. So figure the more in the paper after this is still the first paper. The paper after this, I'm going to go into as far as the importance of having quantum data to begin with, if you're doing QML, and the likelihood of having advantage if you're starting with quantum data, although you can do certain aspects of classical data with it. Now with this, you see the penny lane simulator in blue, and then you see the orange Qiskit and then the gray Qiskit. And this is basically, for test accuracy. So this whole thing with ResNet 34, penny lane simulator, the best case is this, and this is what they reported. Now here you can see the table. So the first two, this 89% and 92% in accuracy in GoogleNet and ResNet 34 is the original graph that I showed from the first experiment. Now everything else here, you can see how it lays out, is basically they're saying quantum transfer learning model with penny lane default simulator has the highest. So this is the 97%. So it's an interesting paper. Probably its biggest claim to fame, it's kind of like the first to be, they say, to our knowledge, we're the first ones doing this specific type of thing. So it's interesting to see. Because, if you were to lay this out, to understand it, starting at the bottom. So you have modified ResNet 34 architecture, variational circuit, selected learning parameters. Now in number 2, it's important. They say a reasonable data size. That's huge for training and testing, quality of data, quantity of data. You have to consider all these specific things. And then you have, quantum computing for dimensionality reduction. So that's the purpose that they're using. And then up top is more or less the summary, where you're using penny lane simulator over Qiskit in these MRIs, and basically its accuracy of showing, is it yes, no, those types of things, with the individual MRI images. Now, the second article is the one that I'm really recommending for anybody that wants to get into quantum machine learning. So in this case, it's They say quantum machine learning will be the natural model to learn, infer, and make predictions for quantum data. So that's a big thing these days is we do not have exponential quantum data yet. However, we do with classical. And as this progresses is basically what they're saying. Now, this inductive bias is an important principle. It says, is any model representing only a subset of functions naturally biased towards certain types of function? Now, the goal in any type of quantum experiment to get advantage is they say to use this inductive bias that is inefficient to simulate with a classical model. And they detailed pretty well, as you see. So I labeled these A through F. So these are more of the opportunities. So in quantum chemistry, they're saying to use QML for simulation. So this could include molecular ground states, equilibrium states, time evolution. And each of these are, likely huge areas to go into. And then you also have material science, quantum phase recognition, generative design with a target property. And again, this is the second paper. This is the Los Alamos National Laboratory. They did a very thorough job in explaining where it is today and where it's going. Now, for learning, it can actually be used to learn quantum computing error correction codes, optimize quantum circuits, compiling. And then for coding, you could use it for syndrome decoders, performing quantum control. And then for QML subsets, for QNNs or quantum neural networks, generative modeling. And then it's also, for shot frugalness. Stochastic gradient descent is from regular machine learning while limiting the number of shots. So this means if you have a task, you don't want to waste resources, number of shots, time, and money. Now, where we are now is called the noisy intermediate scale quantum computing era, NISQ. Now, the paper that I shared from last week is this Google paper, and Los Alamos National Laboratory recognized this paper as having substantial quantum advantage with this previous Sycamore processor from Quantumadvantage back in October 19, but using quantum machine learning. So this is the whole thing of using quantum sensing, quantum memory, quantum algorithms, quantum computing, where the noise of this noisy Sycamore processor isn't quite as important. It's not the principal component when they're doing their quantum machine learning. So to fix these things, so ideally, as we go into, as you see on the bottom, the second step is this fault-tolerant quantum computation. And it's thought by some that we'll likely see widespread and critical use of QML even in this era. Now, ultimately, getting to error-corrected quantum computers is likely going to take significantly longer time, where we can, see the error, correct the error, that type of stuff. Now, the ABC in the triangle here, starting with A, these are techniques, because we're going to be stuck with some error for a while, is QML models where the position of minima does not change due to noise. So I'm going to share in a subsequent slide here, some diagrams that show the effect that noise has on, the results. And then in B, exposure and measurement scheme that filters signal from the noise. And then in C, shallow quantum convolutional networks, QCNNs. And these are the main three things that they said in this current era of, noisiness. So these first two, NISQ and FTQC, is basically, these are the techniques we're going to use to get better quantum advantage with our current hardware. Now, as you can see here, these three different phenomena hinder the quantum machine learning trainability. So the first one is you have an abundance of low quality, local minimum solutions. So this is just inherent to how quantum processing is that, distinguishing between the two local minimums. Now, barren plateau is this phenomenon where you get exponentially flatter. So the solid line is actually bad in this case. So the ball rolling, you want a less narrow trough. So the types that happens is basically noise-induced barren plateaus. You have quantum neural networks that generate too much entanglement, and ignorance or the lack of sufficient inductive bias, which I mentioned before, and the solutions from before too, these quantum convolutional neural networks, and then 2, 3, 4, 5, clever initialization, pre-training, and parameter correlation. So this is in the age of noisy hardware. And you can see how it's hard, right, to get quantum computers with high qubits, because the higher you go, the more likely you are for barren plateaus. And then also, noise kind of expedites things as well. So you see hardware noise in this bottom one is from decoherence and statistical noise. This what's referred to as shot noise. So this is basically in nature, there's different types of shot noise, but typically electrons it's this thing that you can actually, in other types of quantum imaging, you can go subshot noise. But basically it exists nonetheless. Now, number one at the bottom, noise causes a deformation of the inductive bias of the model. So, and number two, an effective reduction of the dimension of the quantum feature space. Basically everything that you're trying to do quantumly to get advantage, also known as quantum supremacy or quantum advantage, is working against you. So that's what's hard in this era with noise. And then barren plateaus, I believe we're going to continue to see that. Now, a good diagram that they put here is basically, it's this interplay. So people think of quantum separate. When you talk to a lot of people at conferences or events, I was just at one yesterday, is that they don't realize that there's a lot of hybrids that are going to come out of this. So in this case, you have a classical data set, you have a quantum data set for a QNN, quantum kernel to get the prediction. So it's one of those things, and here this is the perfect illustration. So classic data set encoding, quantum data set, your QNN, classical optimizer prediction. So in these cases, you're picking. The whole point in switching to quantum or implementing quantum with hybrids is to get an advantage. So you can see in some of these things, such as tamed entanglement, if you have too much entanglement, it can actually be not good as well. And then obviously you really want to research. So if you want to do quantum, working for a company, is you really want to research things that are specifically really hard to simulate today, classically with the best classical computer. And of course, a lot of these other things are similar to classical, as you want really high quality data sets, low training error, noise resiliency. But like, again, I would say that this is one of those resources that you just don't come around too often. And as far as quantum machine learning and the way that they're, forming conclusions on it, and with some other papers that's been covered, is basically it's likely going to play a huge part in quantum tech moving forward. So there's three different paradigms. Okay, so some of you probably know this. Supervised learning, this task-based, is the most common. The less applicable, unsupervised, which is data-based, and reinforced learning, which is reward-based. And basically, the advantages using quantum with supervised learning is resiliency to noise, greater chance of getting quantum advantage, and then this mapping states in different classes to distinguishable regions of Hilbert space, and then good generalization. So their conclusions, so this is the Los Alamos National Laboratory conclusions, is basically this. Data, from quantum mechanical processes is more likely to see exponential quantum advantage in machine learning. So a lot of things, you're going to start to see a lot more quantum data. You're going to see prospectively, and that's what a lot of people think, we already have quantum algorithms, better quantum hardware. And they say, and specifically for QML, from hidden parameter extraction, that's a certain thing that they say a lot of people, that's a good kind of place to start, hidden parameter extraction. Now, this exponential quantum advantage there's two things. There's sample complexity, and there's time complexity. So they're saying it's sample complexity where you have quantum sensing, quantum memory, quantum computer, quantum algorithms too, is that's a bigger focal point than with time. And then in later dates, it's about capturing quantum data from nature directly via transduction from their natural analog form, converting it to digital. So again, great paper. This one I came across maybe 6 months ago, but it's actually, so the title of the article is called The Big Table of Quantum Artificial Intelligence. Now, the things that stick out, besides if you want to research this further, you can go to their website, is this whole CQ, or it's called CC, CQ, QC, QQ. So it's arranged basically by types of data, and then you have types of algorithms. So CC, classical machine learning problems. CQ, classical machine learning algorithms working in a quantum environment. QC, hybrid quantum classical systems using quantum techniques to solve classical machine learning problems. And then QQ, quantum learning environment, learning agent acting in quantum environment. So this is the first half of the chart. So it goes from 1994 to 2011. So the thing that sticks out is the number of supervised learning in the first column. And then as you go to the right here, you're seeing, all of these CCs, CQ, QC, QQ, and most, if not all, are QC. So this is just how it's been through 2011. Now, on this page from 2012 through 2016, you see a very similar trend. Lots of supervised learning. You also see QC taking most of it, if not all, where it was probably a QC paper, and then they also did something that was classical machine learning with it. And it's just something to keep an eye on. But basically, quantum machine learning, and you can see in the table, they call it table 1, quantum machine learning. So this one, I believe this article was a 2016, it came out, hence, it's the end of the chart there. But definitely check that one out too, and then easy references to, find all these things. Now, the LANL, or Los Alamos National Laboratory paper, thought very highly of this, is that, it said it got significant quantum machine learning. Now, I covered this last week, and I want to look at this again, and it's basically saying using quantum sensing, quantum memory, quantum computing, quantum algorithms, is that the primary issue in this noisy hardware era that we're in for quantum is not the principal component. So the principal component in this third column, it says, is part of the superposition with the highest probability. And so that's, as far as I've researched, I haven't found anything else, but basically there's all these tricks you can do, and Google, this is kind of like a redemption because it uses the original Sycamore quantummadvantage processor, but now it's quantum machine learning. And yes, nobody wants noise, and yes, it would limit this too, but in this specific case, I'll show you the data, it's actually quite well. So here's the data. So we're seeing that blue line on the left one is basically, if you look at the fourth point, the number of experiments it took classically was between 1,000 and 10,000, 10 to the 3 or 10 to the 4. Now, if you look at the blue line, you're seeing between 10 and 100 number of experiments needed for this, say, the end system size of 8. So, like I said, like the LANL paper didn't really go over it too much, and we all know that noise isn't good, but this is it appears to be a good step forward, and maybe even great, using quantum machine learning to overcome some of the limitations of just standard quantum hardware that you wouldn't necessarily implement. And then on the right here, you see quantum separates two symmetry classes, that's the top row. And then on the bottom, conventional does not, so this specific. So the devil's in the details, and going through these papers. So this paper, this third article, was originally December 2021 between the three, so Caltech, Harvard, and Google. And then Google came up with something in the middle of this year that basically simplifies it, makes it easier to read, and kind of like even draws more conclusions off this too. So expect a lot of QML. So this I share every time. So basically with neuroimaging, you have to keep in mind of image formation, image computing steps. So where chemical Q device will likely be is with detection, sensing, reconstruction algorithms, and then enhancement, visualization, these types of things with QML or quantum machine learning. I shared this last week. I would suggest anybody take a look at it. I'll post this on LinkedIn. You can click through the links. So I've got 19 quantum sensors. So, and I'm going to elaborate on this more. You also have quantum imaging techniques such as subshot noise imaging, quantum ghost imaging, and quantum computing. Kind of the biggest news most recently, you'll always hear me share the National Science Foundation 2023 Practical Quantum Computer. And then so this is a Bloomberg article from last week. I think it was on the 6th. So the president of the United States took a tour of the factory at IBM. IBM basically announces $20 billion more, and this is part of the CHIPS Act to keep a lot of the electronics manufacturing, quantum computing, and other things inside the US. The highlight is obviously, and it says in this article from Bloomberg, is they take the President Biden to go see a quantum computer. So for those of us who have been in this through the thick and the thin, this past year and many other people, many years before that, it's just good to see, because it takes a certain level of confidence in your technology to, present it to people of renown. And, it's just a very exciting time that, that a lot of this is just, coming to, even early applications in quantum sensing and in quantum computing. The one that sticks out to me is the photonic advantage, Xanadu. So that was a June 1st, 36 microseconds and 9,000 instead of 9,000 years. And then also the NVIDIA, and I'm going to talk about this a little bit later, CPU, GPU, QPU hybrids. So a lot of this is going into specific medical fields, such as current machine learning approaches with neuroimaging. So here are the two besides quantum sensing. So these are quantum ghost imaging, subshot noise, and it's basically separating photons, and they're still entangled, and you get inherently on the left you get faint images. So this two that's not showing up well, it's dark, and then they use a neural network to kind of clean it up. And then on the right, so this is for absorption spectroscopy, and this is separating the top rainbow from the bottom rainbow. One seeing the sample, one is not. So that you're getting, with entanglement and coherence, that's the secret sauce, the quantum advantage. Anywhere from quantum sensing, quantum computing, everything. Now, for those of you who don't know, so there's lots of, and some of these reports have come up in previous, discussions too. So you have, glaucoma affecting Alzheimer's risk. There's a lot of research, obviously beyond just neuroimaging, that can help, and my specific field and others as well, including understanding if Alzheimer's is autoimmune, and then newly discovered proteins or molecules. Now, if you'd like to join an Alzheimer's disease organization, here's some of them. So obviously some are bigger than others, but they have specific purposes. So it's not like this is better than that. So you have a fund, the Cure Alzheimer's Fund, and foundations. The biggest is Alzheimer's Association, but it is something to keep aware of if that's something you want to get into. So all the decks are up. So there's a deck and discussion for each of these. Last week, this QML. So QML is likely going to be a somewhat big topic in quantum tech for a while. because it incorporates hardware, sensing, algorithms, memory, that kind of stuff. Now, the specific problem is that machine learning for neuroimaging today produces conventional multi-contrast, multi-dimensional, and multimodal results. Now, the chemical Q device quantum machine learning solution, and this is what I'm going to be focusing on, is basically with other potential collaborators, is using the optimal sensor, algorithm, computing, and even quantum memory, which is, they say, is likely going to make its way into computing. So in specific, this one keeps kind of showing up. So it's called quantum phase sensitivity detection, QPSD. So the specific application that they used it for was to remove noise in audio recordings. However, they say that this is going to wind up in, it's called vector magnetometry, which is basically sensing magnetic information from live subjects. There's a number of these good quantum diamond sensor papers that help with proximity. Basically, the closer the sensor is to the live object. Mixing, so this form of mixing, it's an MIT paper. It's basically saying all frequencies are detected, accuracy and spin. So for the algorithm in this specific setup, I'm choosing Classique's quantum algorithm platform on AWS Braket. If it's needed for reconstruction in the image formation phase, there's MIT's quantum medical imaging algorithms as well, these reconstructions. So for computing in this specific application of quantum machine learning, I'm choosing the NVIDIA CODA CPU, GPU, QPU, and they say for 287 times speed up in end-to-end VQE, or variational quantum eigensolver. And for my second option, I'm choosing AWS Braket's hybrid jobs. So this allows to send a specific task and to do most of it conventionally, and then the harder parts, or the parts that benefit from quantum mechanics, on quantum hardware. Now, so this is basically the focus with chemical Q device will be with quantum machine learning and piecing these things together, these components. So, and quantum sensing, quantum algorithms, quantum memory, quantum hardware. It's also a potential to create new quantum sensors. So basically, I talked about this one, the quantum phase sensitive detection. And it said this, so this is the one for vector magnetometry enhancement. The specific paper focused on audio noise, but it seems like this article has a lot of upside to it. It was in Nature Communications. And, it lists other potential areas for quantum sensing that other people will prospectively go into. Now, for those who haven't read any paper on quantum sensing, I would highly recommend this. So it's called Millimeter Scale Magnetography of Living Rats with Thoracic, I don't know how to say it, but it's for sensitivity and proximity. So it's a Nature paper, and it gives supplementary information how to get better sensitivity for this type of sensor, their future directions. It's a very thorough paper. Now, the all frequency detection is this whole mixing thing. So when you see this diagram, the green on the top and the red on the bottom, that's fluorescence. So it's interrupting it or incorporating mixing with it using these control sequences and they say that you can get this, all frequency detection. Now for accuracy, this is called, this third one here is basically they took a nano diamond ensemble. There's lots of things that are surrounding just the nitrogen vacancy diamond with machine learning to get better accuracy. And then this one on the bottom right, readout noise. So this is called super radiant spin amplification to help decrease readout noise. So as far as hardware, this is what's likely going to happen. So IBM's roadmap says late this year, 400 plus qubits with dynamic circuits. Now, keep in mind, other experts have said for 2023, we'll start to see some really cool stuff in quantum. We have some stuff in quantum annealing and just, bits and pieces here and there. But what's interesting with this will be how much noise it has. So if they're going up to 400 qubits, Is it significantly less noise? Does it leave noisy intermediate NISQ, which is this noisy era that we're in for the powerful quantum hardware? Now, the other gate-based option is ion trap. This is IonQ. So it seems like they're sticking with a lower qubit, arranged qubit and gates for this dynamic and flexible system. So it'll be interesting. Obviously, I think they have higher than that. But Quantinuum, which is ion trap 2, they have high quantum volume, which they're probably doing it on lower qubit systems and with lower noise. So noise might trump qubits, which it probably is right now. And then D-Wave is interesting. They've been around since 2000, so over 20 years. And then they have quantum annealing that they sold in 2011. Now they actually started off with gate model platforms in like 1999, 2000. However, they quickly switched to annealing. And then now, so you'll have these hybrids. So here's your hybrid. So it'll have like a CPU controller. And then say, for instance, you'll have your quantum annealing and now quantum gate based. I'm not sure if that's ion trap or superconducting qubit. Now, why this all matters is I try to, pay attention to all the compound annual growth rates out there. The one for, global AI and medical imaging market, they say 45.68%. Quantum computing, you can see the second one is 33%. That's a good average for quantum computing. And then you also have, NSF saying this practical quantum computer for next year. And also with the first one, this neurology is accounting for they say the dominating share of the industry. So figure very high compound annual growth for neuroimaging, and this is used for diseases such as Alzheimer's. So this next slide I've shared and I've updated. So the chemical Q device mission statement is to improve neuroimaging techniques utilizing quantum technologies for better sensitivity, signal strength, and or resolution, leading to advanced prediction in neuroradiology for Alzheimer's disease. This includes quantum sensing, algorithms, and computing, ideally, or winding up at MRI, PET scan, CT, neuroimaging techniques. Now, the roadmap that I kind of alluded to before is basically using QML, sensing, algorithms, quantum memory, quantum hardware in 2023 to develop, improvements in neuroimaging utilizing medical research collaboration. So, okay, so we're going to switch over here. And then, okay, so we'll use some chat, and then, let's see. You should be able to unmute yourselves. It's just very interesting because a lot of these people, I see Philip here, Blahi, the other Philip Nikolaev, kind of go with this, quantum journey. And like I said, it's just many people said 2023, a big year. I think even last year, the way things would go, because, basically last year, partnerships, this year, kind of more or less working out the kinks, as you would. And then, so we have other returning people here too. We should have a couple pages. And so would anybody like to unmute yourself? And then I see some, okay, so yeah, so we got chat, and then let's see, you could either unmute yourself. I'd like to see some kind of familiar faces here. Sounds like, some people are familiar with quantum machine learning. And then, yeah, so like I said, you're free to, okay, go ahead, Ron.
Is anybody delivering these diamond vacancy sensors as commercial product at this point?
You mean for applications or just to use with your own research?
Either way, I mean, if you're looking to build some apparatus or push the research of this neural imaging stuff, um, do you at some point build a lab or a facility where you can experiment with the hardware and specifically with these quantum or these diamond sensors, are they being offered commercially like in arrays? Some of the images you showed, that it appears, it would suggest that they're using many diamond sensors to image something. So are those devices that are available, or are they just all,
Yeah. So
everything is a one-off in somebody's lab somewhere?
yeah, and like quantum diamond sensing or diamond quantum sensing, it's been around for a while. I've come across CT schematics that they say they use diamond sensors. So for everybody that doesn't know, you take a diamond and then you omit carbon and you insert nitrogen, and that nitrogen vacancy, when it's properly aligned with microgenerators, gives hyperpolarization. And this is it's basically good, very good results that being used anywhere from magnetic, electric, mostly magnetic. I've seen diamond quantum microscopes, these types of things. And then you could use it for temperature and force. It's by far what it looks like compared to OPM and SQUIDs, the most versatile. Now, as far as the companies, there's a big company called Element 6. And as far as what they hand over to you, I'm not quite sure. But I want to say there's at least 4 or 5 others that are in this whole business of making quality NV center diamonds for your research applications, and then you're doing with it as you please. So yeah, and I would say we're in the early application phase with diamond quantum sensors, with the Nature article with the rat's heart in millimeter resolution instead of centimeter resolution. That paper has an abundance of information too. And some of the other ones too. I mean, if you type in diamond quantum sensor, you'll find a bunch of material, on the internet. And they wanted, even back in 2009, to use these as little probes at the tip of a rod, like an MRI, but just really small. And then a lot of these papers mentioned miniaturization is going to be a huge thing, to use them on the end of both ends. It's endoscopic and then the other one too. So yeah, I as far as, because you can make your own too. There's 2 papers out there that basically tell you how in specific to make your own diamond quantum sensors, I think from relatively pure diamond. But yeah, that was my understanding, is basically a lot of these are basically you're buying them and then using it for your specific application. But I think that's the most common, because there's phosphorus, silicon, nitrogen vacancy. You could do different things with the diamond too.
You mentioned that you've seen a diamond sensor based microscope.
Yeah, there's microscopes. There's
So those
another.
are commercial products that,
Yeah, they have CMOS diamond hybrids, diamond sensor hybrids.
okay.
Yeah, there's many things that have been. It's not a new field at all. So there's many different manipulations. I think with it was an electric field microscope, so there's an advantage with electric. But that's the thing, is the versatility of it all, and then also biocompatibility. Diamonds are inert, and anything that touches humans or other biological samples or in vivo. And they keep improving too. So
So
for instance,
if you have the budget, you can go out and buy a diamond sensor based microscope from somebody.
commercially,
Yeah, and so the next question, if you know, the next question is it in the same realm of owning a tunneling electron microscope? And
I don't know about that. I mean, the biggest issue, SEM, TEM, those tend to be like, as far as resolution, like nano, whereas the rest of fluorescence is an order or two magnitude lower. But yeah, I came across that quantum.gov has this paper called Quantum Sensors Coming to Fruition. And then alongside the other quantum sensors, they give it a really nice feature as far as what it's been used for in research. And, you know, um, I guess you would start off with whatever you want to do. Do you want electric field, magnetic field? Do you want, there's some inherent advantages with preservation of signal with magnetic, but they're always together, like the right-hand rule, electric, and then the, magnetic around it. But yeah, I encourage everybody to take a look at that. And then there is a paper out there. If you typed in Nature Diamond quantum microscope, as far as like these other applications, and again, these types is the specific ones that you typically have to pay for subscription. But for $30, think about what else you can cancel. And I see a number of people on here too. You should be able to, let's see, basically, I see Virendra. If you have any questions, feel free to come on.
Hey, Dr. Kevin, thank you. No, I'm good for now.
Okay.
It was a lovely lecture and lovely presentation. Thank you.
And then some other people here too. We got some new people. So Maynard, you could come on. And then if not, we do have, so Bahar, so I think you've come to the last 3 or 4. Go ahead.
Hey, thank you for your presentation. It was awesome, as always. I was just thinking, in your own company, if you have any results, software and hardware that we can see, we present that.
Yeah, I appreciate. I keep it up to date with most of that. I appreciate that. So we could connect afterwards. And then anything else, Bahar?
No.
Okay. And then I see we have David on. I'm kind of guessing which David, but if it was David Shaw, that would be UK time, which would be a little late. But you can come on, David. And then I guess, okay, as we see here, so Balahi, you're free to come on as well. And does anybody else want to share anything kind of on the medical side of all this?
I'm curious. Hi, Kevin. This is Jacques from Dockley. I want to thank you first for inviting me to this, and this is fascinating. I am curious of the actual applications of this type of imaging, if it will, will advance the medical community to a certain degree, because right now the images that they're using, like, MT CAT scans, X-ray, will it be, it's on a scientific standpoint, it's amazing, but on an economic standpoint, will hospitals be able to actually utilize this? Because I'm guessing the cost of using sensors like that are not cheap. And the science is still kind of new. I'm curious, like, would this be, like, in the medical community, would they accept this right away? Or do you feel that in another 20 years, this might be applicable in like hospital systems and in imaging for doctors to be able to diagnose or better diagnose such neurological diseases like Alzheimer's? That's just my thoughts.
Yeah, I appreciate that. I mean, for me, it all goes down to it's called analog devices, and it's the medical image processes. So I shared it here. I didn't spend too much time on it today, but basically in image formation, you have detection, sensing, and then you have reconstruction, like algorithms. And then as far as the diamonds, they're typically nano, they're very small. So it's just at your specific area that you're looking like. So it's not like the Hope Diamond, these types of things. And what I also think is, basically with any emerging technology and, quantum hardware results, the whole thing is thought to save time in the sense that if the problem is quantum mechanics, it can solve it in a much shorter period of time than conventionally, if that's even possible. The exponential advantage comes through quantum mechanics. So you have quantum bits and you have entanglement and superpositioning. So with entanglement, the more qubits in a quantum computer, the more possibility for advantage. At that same time, you saw with the barren plateaus and other issues with more qubits, as you get more noise or other things that you don't necessarily want as you go up in the number of qubits. So the second paper here with the quantum machine learning is basically saying if you can convert everything to quantum, so you start to get exponential quantum data, measuring on quantum sensors, quantum mechanics, to keep the the memory quantum, algorithms are going to be quantum inherently, and then quantum computing too, that's your greatest chance for quantum advantage. So in the near term, that's more like paper number 1 with hybrids. So where they use transfer learning, so you're cutting off the end and inserting a quantum component to your process, your programming process. So I think that with hybrid QML, which most quantum machine learning will likely be in the next, at least next year, is that you'll have little bits and pieces of quantum technologies, and people will just start calling things, this doesn't really matter, but instead of quantum AI neuroimaging, maybe just quantum neuroimaging, where AI or quantum machine learning neuroimaging or QML neuroimaging, whatever you want to call it, is inherent. And then you start to, less ML, less AI, just quantum this, quantum that. But there's many things out there. So NVIDIA's process, it's hybrid. So it's called CODA, QODA. And then so it promises, CPU, GPU, and now QPU. And they say people are already starting to work with it. But figure the CPU will be better at many things. The GPU will be better at other things. And then your QPU will more be like a GPU and be better at other things too. So that doesn't mean, quantum won't be a huge thing. It just means for specific problems that can be solved quantum mechanically, that makes sense, having these hybrids. And I haven't heard of a quantum computer that runs on its own. I think they all need classical controlling.
Yeah, and it should be pointed out that a QPU is a great idea, but at the current moment of the technology, it's basically a socket into some cloud-based service, whichever one that you want to connect to. So to answer the question is, will it be short term before things like hospitals have these hybrid quantum solutions? It's all going to depend on what the stuff in the cloud does, whether or not they. I mean, there are people who are getting work done, like with the D-Wave machine, for optimization problems. But is it going to come down to they're spending a lot of money, so to utilize that resource. So you have to be working on a project that is of such scale where small increases are still worth a lot of money. So does that map to using a quantum system to analyze one individual MRI? Hard to say.
Yeah, I appreciate you bringing that up, Ron. Now, big news is in cybersecurity. So you have to, well, number one, you have to think about the patient. So if you're using quantum sensing, quantum computing, algorithms, new stuff that could potentially have negative outcome on a patient, that's a concern. For something more pressing like the cybersecurity, Sandbox AQ, I received my first ever kind of quantum advertisement on my LinkedIn this week. It just said Sandbox AQ. It didn't say quantum, but that's what it's a Google spinoff. But in that case, where you're using post-quantum cryptography algorithms on conventional hardware to prevent against future attack. And the issue with that is basically the steal now and decrypt later. So in theory, if China or whoever has an awesome quantum computer and they can take it today, even though they can't decrypt it at a later time. So that's the thing. And it's the same thing, especially for patient data. So Sandbox AQ and Mount Sinai Hospital in New York have a partnership with this. And IBM and Cleveland Clinic have a 10-year agreement, which will likely include security too, but quantum and other things too. So yeah, it just depends. And I think that's a good question that yes. So Jacques, so this is Dr. Lee, is basically, what part of this process, makes the most sense to use with quantum. And with these papers, it's basically saying, don't even waste your time if conventional is close. You want to think about something that'll hold its ground for 5-10 years. So this Google, Caltech, Harvard paper from December 2019, or I'm sorry, 2021, where it's QML and not just the quantum computer, appears to be on a really good track of basically dealing with noisy hardware. But yeah, as far as the things that actually, touch patients, these types of things, there is FDA, there's approval, these types of things, but the government has quantum.gov, and that's 21 organizations involved with quantum. So yes, there's going to be regulation likely, but as far as the NSF, it's like they were the first to fund quantum technologies in the early 1980s. So it's just one of those things where yes, we'll have regulation. But we have some momentum on the government and industry. IBM with the $20 billion, for New York with computing, and President Biden is staring at a quantum computer. So it's a lot of connecting the dots. So it's very interesting, because last year people said people weren't even concerned about 2022. They were just concerned about 2023 because they knew it needed some more time.
A couple of things I wanted to chime in also, Kevin. Here. So, it's a very good question which is asked, and normally we get that question in every single webinar, every single discussion we come to, and that has a connotation of, okay, what am I getting additional in terms of going through quantum? So there are bottlenecks, there are hurdles. So there are three angles on which we can address the question. One is the technology part. Second is, as you said very rightly, the legislation part. Third is privacy, HIPAA, and all those concerns. So all those things taken together, but first and the foremost is, where is the technology headed? Now, technology is definitely in the right direction. And as we talk every time, AI, ML, it took whatever 25 years to mature. Quantum is way ahead in the game from that angle, because parallelly, it has taken its toll in terms of going through those years. And there is a good basis and good amount of algorithms to write on using AI, ML, and all those things, and all those pieces of the puzzle, where quantum can take it to next level. So is it going to be pure quantum in the next coming early years? No, it is going to be the hybrid, because hybrid is where the TCO, cost, and everything lies together, where it says that, yes, if I can look for something like commuting to office, and I say regular good cars, reliable cars like Hondas and Camrys are good enough, but then I do have to look into account now, do I only want to run those cars, or I want to bring an environment equation into the picture as well? And the simile to that in case of AI, ML, or quantum is, when it comes to the legislation, that's one piece of the story. But let's jump to the third piece, which we were talking about, HIPAA and those privacy considerations, encryptions, which is a real good crux of quantum, where it has even an additional edge over everything. So that's where we can take advantage of that. Otherwise, as I said, when it comes to an office commute, a good reliable car is good enough, then why should you spend more? Well, there are those reasons to spend more. Then the good question lies about technology, which comes up is that if AI, ML, and all those regular things and sensors, can they give me a good enough result-oriented situation there, or still I want more out of it? How far I want to go, because I'm sure people have come across, when it comes to, for example, MRIs or X-rays, they have their cost involved. So some companies nowadays are even taking a stance where they give you a very mini subset of that optimization, so that then you decide, hey, I've already spent this much. Do I want to go all the way through for MRI for hospitals? Because cost, insurance, all those things are into play as well. And that's where those companies are making their case that yes, not every particular case needs a full warranted MRI, where we could have a 10% level or 20% or 30% level, depending upon the first piece of the puzzle seen. Then we say, okay, I want to go deep into this angle, that area, that place, or that piece of the organ, and go further from there. Similarly, coming to that and going for the third piece of HIPAA considerations. Now, where are we now? Because we have seen in the recent days or years or recent times, I would say, some of the crime also basically push people to that level where all these considerations, data, and all this privacy and everything has to be maintained more religiously. So that's where they have those pluses, they have those minuses. So it's just a balancing equation people will have to do, taking these few factors into account and saying, yes, it makes sense to go for this kind of piece for full technology, or through the legislation, or for quantum or hybrid quantum. But the answer lies there. But the crux of the story, well, it will not take 25. It may take 5 to 10 or whatever number we may want to say. And then the affordability. But as you rightly said, government is pushing a lot of funding into quantum, because one piece of the story is very clear. They want to be at the edge of quantum technology, unlike AI, ML, where there are so many front runners now. So they want to take that edge in quantum. That's where I would rest my case. Thank you.
Yeah, I appreciate that. And even the big table of quantum artificial intelligence, I think one of those papers went back to like 91, as far as the whole CC, CQ, QC, QQ. So yeah, I think some other things are playing to its advantage of, maybe not taking that long. And I've heard, in 2017, there was people thinking that they were so close to just figuring this whole thing out. So it's been through, and I'm talking about computing. Now, the medical data accounts for 30% world volume out of all data, and then it says it's going to grow at a compound annual growth rate of 36%. So figure wearables and IoT, in-home, all this stuff. So yeah, it's a huge field.
Yep.
Yeah, I agree. I mean, recently the Nobel Prize announcement gave a boost to the quantum field, and a lot of people showing more interest in this field because of recognition quantum is getting. So I think more to come. More funding will be allocated based on this, I think.
Yeah, and I'm glad that you brought that up, because if IBM's working on gate-based superconducting qubit, and the physics announcements was for photonics, primarily quantum photonics. So you have psi quantum, Xanadu. So it's interesting because these Nobel Prize announcements don't mean nothing, right? So you have to pay attention as far as like, because it's still not clear to me on the hardware race because ion trap. I don't hear too much about neutral atom, but yeah, I think the one in theoretically most powerful gate-based superconducting qubit, the one that's best in Nature and other big articles is ion trap, as far as it actually like working to a greater extent. And then the one that everybody wants is photonics because it's room temperature. So, you know, you kind of pulled all these together as like, there's a lot of other people involved in quantum. But yeah, that's what they said. It's for photonics with quantum. And then feel free to add to the chat. So there's so Ron added some stuff here too. So Ron's got experience in compiling, and then Bill posted a link for this quantum diamond microscope. There's other applications too. So in the deck that I have, I included 19 links to diamond quantum sensors, and then the rest of it is diamond quantum sensors. So there's that. So yes, so you know, Anna has a meetup here too, or her own meetup, and a series of the Nobel Prize is in progress. Okay. Is there anybody else that we haven't heard from that would like to either you can unmute yourself or come on?
I'll just mention, this is Bill. I thought it was a good talk. Got a wide experience, at least seems like you're researching this every day. Is something that I personally do as well. My focus is mainly on image processing side. You mentioned medical imaging. I sent you, I think maybe some contact information. But you know, even as far as what some of the challenges from the AFRL are pushing out is looking at imaging, quantum imaging, to assist with overcoming some of the problems of standard, you know, equipment that loses focus when two objects are fairly close together. And they're talking about space debris, and we're talking about space debris collection, identification, you know, astronomy, image processing, etc. I did see a talk at IEEE from a company out of Germany who's using QCNN's quantum convolutional neural networks, although they had the term quantum classical convolutional neural networks. They added an extra C in there, but what their purpose was, even though they were working on machine learning, was actually to determine, I think, breast cancer identification. In other words, based on processing images, etc. I myself work in the field of taking, you know, imagery and then converting it into a quantum state and then reading it back out using various algorithms that are available out on the internet. But most of what we see is practiced on simulators. You'll see some practical use on actual IBM computers, etc. So most of the time I spend my time writing algorithms and actually writing gates and everything, gate circuitry, etc. But I think there's a lot of things happening, you know, in regards to what the government needs. They focus, as you mentioned, on sensing equipment and cryptography, right, and quantum internet, because that's where China lays its threat, of course. But I think that imagery or imaging, quantum image processing, I think is a key area. And I think some of your stats that you mentioned show that, is that not only can it be used for astronomy, but also for, you know, assisting, you know, practitioners identify and help the patient better. But thank you.
I appreciate all that. Now what it reminds me of is just like, there's another, I came across another paper too. It's similar to the analog devices where it goes through all the steps of any type of imaging, although it was medical. And then for you, your conundrum, two objects close together. I mean, it kind of reminds me of quantum imaging. So those four parts are quantum sensing, and then quantum ghost imaging, and then quantum substrate noise. Quantum lithography isn't used as much. So, but you know, those are whole setups on their own. And then, you know, quantum ghost imaging is not fixed, but they did a neural network to take that kind of faint original 2 image and then, you know, produce a greater one. And it just reminds, it just hybrids and lots of different technologies for lots of different things. The other stuff, let's see. So I wanted to share some people in, so this is basically a meetup. So Louine, I don't know if I'm saying your name right, but basically the question is, how could quantum machine learning make Alzheimer's, better, or quantum machine learning neuroimaging to make Alzheimer's better? So Louine said prevention, diagnosis, and treatment. And if you'd like to add anything else to that, you're welcome to, Louine. And we had some other, okay. So we had some other kind of comments here too. So Natasha may have been on earlier, but she said early detection, treatment and management. I think Louine, correct me if I'm wrong, you also said drug discovery. And then, so Victor said diagnosis and prevention. Yeah, I always appreciate the feedback here. Now, anything else on the quantum side that anybody would like to share? And then I think, is there anybody else that would like to present anything? And then if not, this has been episode 52. So I appreciate everybody coming on. Didn't miss a week for a whole year. Go ahead, Virendra.
No, I was about to say thank you. Thank you for keeping the tempo on.
Yeah, I appreciate it. And it, like I said, it's good to grow with other people in the chat here too. I've learned a lot. And then, yeah, so Ron or Virendra, you can come on.
Just, another thank you to Kevin. These weekly sessions are so beneficial just from the fact that it's open discussion and lots of people get to interact, and I find that incredibly helpful. So keep it up, Kevin.
Yeah, and I appreciate the feedback. And like I said, I've learned a lot too. I've done a lot of these episodes learning, right? Researching speakers, and there's been CEOs, founders, TEDx speakers, recruiters, directors, the whole kind of thing. Obviously, it's the bent is more towards getting the startup project to work. But yeah, it's still, good discussion even through, that was last October 21, and this is this October 22. And then, was there anything else? I see Bill in the chat. Awesome. Okay. So once again, thanks everybody for coming on. So we'll see for next week. This has kind of been the big push. And then I had a Johnson & Johnson event yesterday. It's like a potential incubator where, people in the city. So it's been a busy and exciting week. Let's just put it that way. So yeah, thanks everybody. Have a good rest of your night, and have a good rest of the week, productive week. Take care. Bye.
Thank you, guys.
Thank
Thank you.
you.
Thank you.
Thank
Kevin.
you. Have a good night.
Nice talking to y'all. Bye-bye.